The whole point of this is to be able to store a floating point number, a number with a decimal in it, right? So like something like 1.3. So what does that mean in binary? We talked about that. So that's tenths, hundredths, thousandths. It's 10 to the 0, 10 to the first, 10 to the second. But on the other side of the radix point, it's 10 to the negative 1, 10 to the negative 2, 10 to the negative 3. So it's exactly like that in binary. To the left of the radix, it's 1s, 2s, 4s, the column values, right? To the right of the radix point is 2 to the negative 1, 2 to the negative 2, 2 to the negative 3. And what does a negative exponent mean? It means you just put that thing in the denominator. You flip it. If you've got a negative exponent in the denominator, you move it to the numerator, right? So that's what 1/2, 1/4, and all those things are. My issue, the reason I'm kind of confused, is I don't really remember when I've covered this in this class and when I covered it in my discrete class. I know I've just covered it in my discrete class, and I can't remember which one I'm remembering. All right, so anyway, so we have 1s, 2s, 4s, 8s. Over here we have 1/2, 1/4, 1/8, and whatever the system is, we do it that way. So if I have a 1.11 in binary, it means I have a 2, I have a 1. I said 1 and wrote 2. All right, so you multiply the column value, column digit times the column value. So I have a group of 2, that's what that's saying, 1 times 2. I have a group of 1, 1 times 1. I have a single half. I have half of 1. That's what that means, 1/2. Not 1 and 1/2. It's I have 1 of these 1/2 things. So I multiply that times that, and I get 1/2. Multiply that times that, and I get 1/4. And I add those things together, I get 3 3/4. So that's pretty easy to do. Yeah, I remember doing that specifically. All right, so fractional, binary, and decimal. Remember talking about this part too. So there's 2 parts about this one that I want to talk about. One is the easy way to do these things. I think my next slide shows that, but that's okay. 1011.1101. Remember those being a mirror image. All right, so what does this mean? This is my 1s, my 2s, my 4s, my 8s. So I have 8 plus 2 plus 1 plus 1/2, 1/4, 1/16. So that's plus 1/2, 1/4, 1/16. So I add all these things together, 8, 9, 10, 11, 11. And to add these, I have to convert them to 16ths. So 2 will go into 16th. 2 will go into 16 8 times. 8 times 1 is 8. So that's 8/16. Right? That's a half, 8/16. 4 will go into 16 4 times. 4 times 1 is 4. 4/16 is 1/4. So those are the same. And then we just add those things together, 8, 9, 10, 11, 12, 13, 13/16. And going over it quick because I know I remember doing it for sure. Another way to do this is we just do this the way we always do it. So I don't really have to add those up, do I? We should know what four bits. We should be able to translate 4 bits into decimal pretty easily. Did I just do that? Oh, yeah. I don't remember. Anyway, 1, 2, 4, 8. So 8, 9, 10, 11, 9, 10, 11. Right. And so what's this part? Why does it feel like I got that wrong just a few minutes ago? That's definitely 11, 8, 9, 10, 11. Yeah. Over here, looking at this, I'm not going to treat it like a fraction. I'm just going to look at this as if it's a normal binary number and ignore the radix point. So I start at the radix point and work my way over, and then just treat that as a single number. Now, looking at that as a binary number, I could see that would be 13, right? So that's 13. So that's going to be my numerator. So I just take that thing and look at it as a normal binary number. That's 13. And then to figure out the denominator, I go 1/2, 1/4, 1/8, 1/16. Wherever this last one is, that becomes our denominator. So 13/16. It's real easy to look at that and say, oh, that's 13/16. We shouldn't have to add up all those fractions. That takes too much time. Now, the other thing was, if you've got something like this, we want to get rid of these trailing zeros. That'll give us a fraction that we can reduce. We don't want to have to do that. These aren't significant. They don't really change the number. They do have meaning, so don't get me wrong there. There are times when you want to keep those zeros in engineering processes and those sorts of things, but you know, as far as the actual value of the number, they don't add to the value. So we take those zeros off, and this will always give us, in binary at least, the most reduced form. All right, so let's get rid of that. How do we convert fractions to decimal? We repeatedly multiply by 2. So I don't think we covered that part. All right, so if we've got something like 12.3, then we're going to have to figure out what those pieces are. It feels like we did that too. I don't know. I'll repeat it too, just because it's good to know. It's good to remember. All right. So if you got something like 12.3, how are we going to convert that? 12.3. We're going to convert it by this side. We repeatedly divide by 2. So 2 will go into 12. 2 times 6 is 12. 2 is 12, leaves with a 0, 2 will go into 6. 3 times 2 is 6, leaves with a 0, 2 will go into 3. 1 times 2 is 2, leaves us with a 1. 2 will go into 1 0 times. That 0 means we're done. 0 times 2 is 0, leaves us with a 1. In reverse order, 1 1 0 0. So 12 turns into 1 1 0 0. This is a long way to do it. You shouldn't have to do it that way. I just put it that way in the instructions and in the notes as a reminder of how to do those. When these get bigger, you might want to do that. All right, so what about the 0.3? We take the 0.3 and multiply it by 2. 2 times 0.3 is 0.6. That's one of our digits. So we had 1100.0. That 0 goes there. Multiply that times 2, 1.2. That 1 is one of our digits. That 1 goes there. Multiply that times 2. Now remember, this goes back to 0 because we moved it over there. So that's going to be 0.4. It's going to be a 0. Multiply that times 2. That's 0.8. It's another 0. Multiply that times 2. That's a 1.6. It's going to be a 1. And notice that the 6 repeats. So when I multiply this again, I'm going to get a 1. And when I multiply that, I'm going to get a 0. And when I multiply that, I'm going to get a 0. And when I multiply that, I'm going to get a 1. And then when I multiply that, I'm going to get a 1 again. So it's just going to repeat over and over and over again. So I know what this number is. 011, 10011, 1001, 1001. It's just going to go on forever and ever and ever. So normally we write that this way with a bar over it. But what we're getting ready to do is put these numbers into floating point format. So what we need to do is repeat these numbers. Don't just write it that way. Now on quizzes, sometimes I'll say, just write it like that with 1 repeat. That's what I'm looking for. And if you write it that way, I know that you know it ends there and that repeats. If you add more stuff onto it, I don't know that you know that it's repeating, and you'll get the question wrong on the quizzes. But when you're putting these things into the floating point format, like we're getting ready to talk about, you have to add these digits in or you'll get the problem wrong. We have to have a certain number of digits for our floating point. And since we haven't talked about floating point, I'll leave that for just a few seconds. All right, so blah, 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 blah. All right, so what is floating point? Floating point is just a way to store things as a numbers like 12.3 in the computer. The computer, we only have 1s and 0s. So what we're going to do, we're just going to break it into pieces. Those pieces are going to be whatever we need for the floating point. So what do we need to store a floating point number? We need to know, we're going to turn this thing into scientific notation. So if I look at what I've got up here and I write it in scientific notation, 1.10011011001000. Right. At some point I need to stop that, so I'm just going to stop it there. Let's see, I don't know if that'll be enough. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's just enough. Times 2 to the, where do we move that? 1, 2, 3. We made that smaller, so this needs to get bigger. So that's 2 to the 3rd. So that's how we're going to write that. So what do we need to store? We need to store this number we need to store this number, and we need to store the sign. So those are the three things that we need to store for our IEEE floating point numbers. So we're going to take our number, write them as binary fractions, take those binary fractions, write them as scientific notation using powers of 2, and then we're going to take that, and those are the three pieces that we need to store, and that's what this is showing. We only need one bit to store the sign. It's positive or negative. Positive is 0, negative is a 1. The exponent is this thing. We're going to store it as in our excess system. We're actually going to store something called a characteristic, not the exponent itself. That gets bigger as the number of bits we have get bigger. So 5 for 16-bit, 8 for 32-bit, 11 for 64-bit. Our mantissa, this piece, we're going to store 10 bits for 16-bit, 23 for 32, 64 has a whole bunch, and the 128 has a whole bunch more. We're really only going to do the 16 and 32-bit numbers. All right, so writing things in scientific notation. You should really know how to do scientific notation. The big thing about it is something called normalized. Normalized means there's a single digit to the left of the radix point that is not 0. So it's single digit. So in binary, what digits do we have? 1 and 0. So which one of those is not 0? 1. So this thing always has to be 1. That's why we're not going to store it with our mantissa. Just like this, we don't need our times 2. We know it's times 2, so we're not going to store that as our mantissa in our floating point format. These floating point formats are exactly, you can think of them as almost like instructions in the LC3. Remember, those are just binary numbers, instructions in the LC3. It's just that some of those bits mean something, some of those bits mean something else. That's exactly what scientific notation is. And it's the thing that's interpreting it that needs to know what those binary patterns, how it should interpret them. How does Java know? How do programs written in Java know to interpret something as a floating point number? It's because you defined it as a double or a float. So that's why it gets treated like a double or a float. If you define something like an int, then Java and the programs you write in Java are going to treat it like an int. But remember, inside the computer, if you just looked at the 1s and 0, you would have no clue as to whether it was a scientific notation number, a floating point number, an integer, a part of a pixel, part of a music data, part of a word processor program, or an instruction. You just wouldn't know. We cannot store 0 in this. We cannot. We absolutely cannot. We'll talk about that. All right, so how do we write scientific notation? Normalized scientific notation. Normalized means that there is a way to, we put it in scientific notation with one non-zero digit to the left of the radix. So let's look at these. What am I looking for? I'm looking for the board. One 0.11.101. The radix goes 1.111101 times 2 to the 1, 2. So it's either 2 or -2. This number, it started out as 7 and then it went to a 1. This number gets smaller when the radix moves this way. This part gets smaller, therefore this part has to get bigger. So if we say that's 2 times 2 to the 0, this goes 1, 2. That's 2 powers of 2. So we add 2 powers of 2 over here. So that's how we do that. So let's look at the next one. 0.123411. All right. So now we look at this and we go, okay, let's just call that times 2 to the 0. And we're going to go 1, 2, 3, 4, 5. So this got bigger by 5. 5 powers of 2. It just got bigger. This needs to get smaller. So I have to subtract 5 from the exponent. So now those are the same. Looks like we went over all this. I'm probably repeating everything I just did. Shouldn't take weekends off, should we? Times 2 to the second. All right, so this is going to go 1, 2, 3, 1.001111. So I either need to add 3 to that or I need to subtract 3 from that. This got bigger. This got smaller. It started out as a 9 and it became a 1. So when the radix moves this way, the number gets smaller. This needs to get bigger. How much bigger? 1, 2, 3. So we add 3 to that, 2 to the 5th. And then the last one, I remember doing these. I do remember doing these. There's too many ones. Times 2 to the negative 4. That's all right. Review's good. This is going to move 1, 2 that way. Right? 1.11 times 2 to the, this just got bigger. This needs to get smaller. Smaller means I subtract. So negative 4 minus 2 is negative 6. Yeah, we did all that last time. All right, so let's put these into triple E floating point format. We're going to store our numbers as characteristics. So that's component, exponent plus excess. That's the characteristic. So inside of our triple E format, we store things as the characteristic. We always add 5 when we're putting it into floating point numbers. So that means add 5, add 15. Our excess is 15 for 16-bit floating point numbers. So we always add the excess when we're storing the number, and then we always subtract the excess when we're bringing it back out. All right. So how do we calculate our floating point number? Write your number in normalized binary scientific notation if it's not already done for you. The mantissa must have enough bits to fill the mantissa portion of the floating point number. So if it's a 32-bit, if it's a 16-bit number, we need 10 mantissa bits. If it's a 32-bit number, we need 24 mantissa. Yeah, that's right. Calculate the characteristic by adding the excess to the exponent, store the sign, store the characteristic, remove the leading one from the mantissa and store it. For most quizzes and homework, we'll write this value as hexadecimal. Right. So here is a number that is already in normalized binary scientific notation. Let's figure out what to do, how to store it. So 1.1110 times 2 to the 4th. So the sign for this number is positive, so we're going to store a 0. We know that's the sign. Characteristic is going to be the exponent plus 15. So 4 plus 15 is 19. Now remember, for 16-bit numbers, we're going to store this as 5 bits. So we need to write that number as 5 bits, 5-bit binary. So 19 is 16, 17, 18, 19. All right, so 0 is what our sign is going to be. This is what our characteristic is going to be. And then our mantissa is going to be this. Now we start at the radix, and we start working our way over. 1, 1, 1, 0, 0. This has to be 10 bits. So we just add bits onto the end of it. Remember, in this form, if I've got 1.111, 0, 0, all these aren't significant. So adding these zeros on the end isn't adding anything to the value. It's not changing the number in any way. So it's okay to do that. But it's only okay to do them on this side. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's our mantissa for this problem. So how do we write the whole thing? 0 for the sign, 1, 0, 0, 1, 1 for the characteristic, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7. So 16 bits. If you need to write it in hex, sometimes I will. We just say 4, F, 8, 0. These aren't that hard, by the way, and they should really just take maybe a second or two to do these. All right, so that's exactly what I just went over. All right, so let's think about going back the other way. We do exactly the same thing in the other direction. So I'm giving you this 16-bit in hex. I won't always tell you it's 16-bit, by the way. If I give you a 4-bit hex number and say, convert this floating point to decimal, you should be able to look at it and say, oh, there's 16 bits there. This must be 16-bit floating point format. If I give you an 8-bit or 8-digit hex number, then you should know that it's a 32-bit. So look for that. I think in some of the quizzes, I don't actually tell you 16-bit. I expect you to know. So if you look at this, C640. C640. Remember, each hex digit takes up 4 digits, so that's 4444, which is 4 times 4, which is 16. So there's 16 bits there. C1100, 60110, 40100, that's my exponent. I know that it's negative. That's my exponent. That's my mantissa. So I look at my mantissa. This is 1001. Remember, you got that 1 point to put back. Right? It's not stored. Now, that doesn't have anything to do with that, by the way. I'm looking right now at simply that piece in the box. 1001, and then I put that back on the front end of it. Times 2 to the, hey, look at that. That's 16, 17. 17 minus 15. Is it 17 minus 15? Or is it 15 minus 17? See, that's always the tricky bit here. We always subtract the excess from the exponent. This one's wrong. So you've got to be careful about that. If this bit's a 1, then this is a positive value. That's another easy way to do it. If this is over 15, 15 is 0, by the way, because if we subtract 15 from the number, we'll get 0. So 15 means 0. That means 16 or anything else is a positive number. So we can look at this and say, oh, that's a 2. 17 minus 15 is 2. Denormalize it. So I'm going to say, get rid of this part. So times 2, 1, 2, 110.01. This is 6.1 half, 1 4, 0.25, or 6 1/4. So it should be fairly easy to do these things. They're not that hard. And this goes through what I just did. All right, so what about 32-bit? 32-bit, the procedure is exactly the same. The only difference is you've got more bits here and you've got more bits here. You've got 32 bits. This is 16 bits, so we've got more bits here and we've got more bits here. How many more? We have 8 bits for our exponent now, for our characteristic. And we have 23 bits for our mantissa. All right? But everything else is going to be done exactly the same way. The big difference is that we have a different excess. Since this is 8 bits instead of 5 bits. The reason it was 15 is because 15 is basically half of what you can store here. 5 bits, 2 to the 5th is 32. If you've got negative numbers, then that means in 2's complement, it would be 15 down to negative 16, right? So that's why the 15 is in there. That's why 15 is what our excess is, because it gives the same range as it would as if it was a 2's complement number. So if we have 8, it's basically half of this minus 1. So 2 to the 5th, 32, half of that, 16 minus 1. So what happens if we have 8 bits? 2 to the 8 is 256. Half of that is 128. Minus 1 is 127. So our excess in this system is 127, and it'll always be 127. The excess for the 16-bit will always be 15. The excess for 32-bit will always be 127. So you don't even have to think about those or worry about those. All right, so let's do these examples. The top one, if you ever see something like that that has a 0.09375 and it ends in a 5 like that, these are going to be even. They're going to evenly work out. So when you're doing your problems and you have something like 0.9375 and you're multiplying it by 2, if it doesn't end relatively soon, you're probably doing it wrong. You've probably messed up in your math somewhere. So 10, 1010, 0.09375. How do we figure out that? We multiply it by 2. 2 times 5 is 10. 14, 15. 2 times 3 is 6. 2 times 9 is 18. 0.1865. Now notice what happened. This is almost always we're gonna lose a digit. This has 1, 2, 3, 4, 5 significant digits. This has only 4. So 0.1865, but this is our bit, so we know it's going to be a 0. Now we do our next multiplication. Please, please, please. I see people do this all the time. They're afraid to do it. Get rid of these zeros on the end. they're just going to take up more time. You're going to have to write extra zeros that you don't need to be writing, and it just makes it look a lot worse than it really is. 2 times 5 is 10, carry 1. 6 is 12, 1, 13. See, it looks like I've already messed up somewhere here. It already looks. See, I can look at this and see that 6 looks wrong. This 3 looks wrong. This should end in a 5 when I'm done. So probably a good idea good that I messed up, because it shows that it's easy to do for one thing, and it shows that you can look at it and tell if you're already messed up. 2 times 5 is 10, carry your 1, 14, 15, 5, carry your 1. See, there's where I messed up. 6, 7. That should have been a 7, 5. 2 times 9 is 8, 1, 8. So 1.875. See, if this didn't end in something like a 7.5 or a 2.5 or something like that, I know it's wrong. I know it's wrong. Right? But anyway, that's still a 0. So multiply that times 2, get rid of that 0. 2 times 5 is 10, carry 1, 14, 15, 5. 2 times 8 is, carry 1. 2 times 8, 16, plus 1 is 17. Carry 1, 2, 3, 3, 0.375. Multiply that times 2, 10, carry 1, 14, 15, carry 1, 6, 7, 0.75. Multiply that times 2. Well, look at this. Does anybody remember what 0.75 is? Just if I asked you to do 0.75 without anything else. Just ignore the rest of the problem. If I said write that in binary, you'd say, well, that's a half plus a fourth. You could look at that and go, that's actually 0.11, isn't it? Technically, we can do that here. This is going to turn into a 1, 1. It's going to turn into a 1, 1 on the end of that. If you get to a 0.75, just say, oh, that's 1, 1, and put it up there and be done. If you don't like doing that, that's fine. Let's go ahead and work it out. Multiply that times 2. We're going to get 1.5. Let's bring it up here. That's not right. 0.75. Multiply that times 2. That's going to be 1.5. So we get our 1. Multiply that times 2. Remember, that goes back to a 0. It's going to be a 1.0. Puts a 1 over here, and that 0 means we're done. So there you go. That shouldn't take that long to do. And you should be able to pretty easily see if you've messed it up. All right, so there's that. Let's write it in scientific notation. Normalize, so we're going to move this 1, 2, 3, 1.010000011. One of the biggest things that people do wrong is writing the number down again and accidentally taking out a 0 or adding an extra 0. So be careful about that. That's something I always like to look for and make sure I didn't mess it up. Times 2 to the 1, 2, 3. Is it third or negative third? Well, this made the number smaller. So this needs to be getting bigger. Right? It's times 2 to the 0. So if this is getting smaller by 3 powers of 2, this needs to get bigger by 3 powers of 2 for it to stay the same number. So there we go. 0, because it's positive. Characteristic, 3 plus 15 is 18, 16, 17, 18. And then the mantissa, 0, 1, 1, 2, 3, 4, 1, 1. All right, that's 1, 2, 3, 4, 5, 6, 7, 8. So I know I need 2 more on the end. That should be 16 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Write it in hex if we need to. 490C. Not too bad. Not too bad. All right, let's do the same thing in 32-bit floating point. Guess what? This is exactly the same. So we don't have to worry about it. It does it exactly the same. All right, so let's say I've got to this point. Now I just want to store that as 32-bit. 0, because it's positive. Now we use 127. 127 plus 3 is 130. Now I like to look at this and think about it as 1, 2, 3, 4, 5, 6, 7, 8. This is 127, isn't it? I mean 128. So if this is 130, I'm actually storing 128 plus 2. So if you break it down into that, it makes it a lot easier. It makes it a lot easier to figure out. Because this will always be something relatively small, because if I make it big, then the numbers just become horrendous and the problem just takes forever to do. So these will always be pretty small. So it'll be 128 plus 2. The rest of these are zeros. All right, what about the mantissa? I have 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, and those go off to infinity. I say infinity, I'm kidding. There's 32 of them, so this needs to be 32 bits. But I don't really need to know. Everything over here is going to be zeros. Once I figure it out and stuck in my mantissa, everything's going to be zeros. So I can just start over here and say that's 4, that's 1, that's 2, that's 1, that's 8, and then everything else is going to be zeros. I know there's supposed to be 8 of these, because it's a 32-bit number, so there's got to be 8 of them. So 4 times 8 is 32. 1, 2, 3, 4, 5, 6, 7, 8, and I'm done. So that's how easy it is to do the 32-bit. They're exactly the same. All right, the 2.71, the only difference is we have to do a whole bunch of multiplications. The top one, the 0.9375, is going to come out pretty even. The 0.71 is not going to come out even. So the difference between the top one, the 10, and the 2.71 is the 2.71 is going to take a lot more divisions. You're going to have to actually physically do a lot more work for that one. For the 0.71, I'll never do something like that on a 32-bit one, because you have to fill up a 23-bit mantissa, and that's 23 separate divisions, possibly. That's a lot. That's too much work for a test. It's too much work for a quiz, really. So all the 32-bit numbers will be like the top one, the 0.09375. Some of the 16-bit problems will be like the bottom one. All right, so let's go the other way. CB40. Wait a minute, we already did that one, didn't we? Let's do the 5112. 5112, that's hex, so that's 0, 1, 0, 1. 1 is 0, 0, 0, 1. 1 is 0, 0, 0, 1. 2 is 0, 0, 1, 0. That's my exponent. All right, so subtract 15 from that, and I'm going to get 5 times 2 to the 5th. How do I know that? Because that's 16. If I subtract 15 from 16, I got 1 left over. That's a 4. 4 plus that 1 that's left over is 5. If you want to write it out, that's fine. This is 16 plus 4 is 20 minus 15 equals 5. So 5 is the exponent. So I look at this and I go 2 to the 5th. I write my mantissa 1 point, because I always put that in, and then I put this number in, 0, 1, 0, 0, 0, 1, 0, 0, 1. Leave off those extra zeros on the end because they're not really helpful. All right, times 2 to the 5th. 1, 2, 3, 4, 5. So this becomes 101,000.1001. This is 1, 2, 4, 8, 16, 32. That's 40. And what is this? Well, that's the number 9, 1/2, 1/4, 1/8, 1/16. 40 and 9/16. Sometimes I tell you to put the ampersand in on the quizzes. So make sure you look for that. Sometimes it's a space. I don't know. Just read the instructions. How easy that was. I mean, that didn't take any time. It didn't take any time hardly at all. And it should be nearly that quick for you all. All right, so here's some for 32-bit. Like I said, I'll never do the 2.71, so I'm not going to do that one really. We already did the 10.9375. So let's do one of the bottom ones just really quickly. BF98. BF980000. So B1010, F1111, 91001, 81000, and then the rest zeros. I don't care about those. I'm done with what I need. Figure out these 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I screwed that up, didn't I? B is not 1010, it's 1011. It's like that didn't quite look right. That makes more sense. Be careful about that. That's look how easy I did that. And I do these a lot. I do these all the time, and I have these memorized, and I messed up B. I usually do it because I'm thinking ahead, or I'm trying to think of other things while I'm writing, and I should not do that, but I do. All right, so 1, 2, 3, 4, 5, 6, 7, 8. Anybody know what that number is? That is 127. Because if I added 1 to it, it would be this, which is 128. So that must be 1 less than that, which is 127. So 32-bit, what's our excess? 127. So what's 127 minus 127? It's 0. So what does that mean for our exponent? 2 to the 0. That's okay. That's okay. That's just fine. All right, so what's our number? Our number starts here, our mantissa part, 1.0011 times 2 to the 0. So this means we don't have to, this is kind of, the normalized form is the denormalized form. They're both the same. I can just get rid of that. I don't have to worry about it. Now I just have to interpret this. What is that? That's 1. What is this? It's the number 3. Where's the 16ths? 1 and 3/16. Let's see how fast we can do the talking. Let's just go ahead and do it. Might be the same one. I don't know. C18 C 0000. So C1100 1000 8100 C1100, and then everything else is zeros. Figure out these 8. 1, 2, 3, 4, 5, 6, 7, 8. The exponent's 4 because that's 3. All right, so this is 127 plus 2 plus 1, which is 130. I'm sorry, that's 128. I'm thinking ahead again. So I'm thinking subtract 127. So that's 128 plus 2 plus 1, which is 131. Minus 127 is 4. Right? Another way of thinking of this is 128 plus 3, right? 128 plus 3, which is the same as 127 plus 4. Right? Those add up to the same thing, don't they? And then I subtract 127, so that goes away. It leaves me with the 4. Basically, if this is a 1, I can look at the rest of this and just add 1 to it. That's the number 3. Just add 1 to it. So that's the quickie way to do this. All right. So what about our exponent? What about our mantissa? 1.12311 times 2 to the 4th. 1, 2, 3, 4. It's 10001.1, which is 1, 2, 4, 8, 16, 17.5, or 17 and a half. Quick and easy. Easy to do. These don't have to be that hard. People complain all the time about them. All right, so there's some special numbers that we need to be able to represent. 0 is one of those. As was brought up already. All right. You actually technically can't store a 0 in this format if you think about it. What am I doing here? How do I do this? What would I have to store an exponent? The exponent can be 0. The exponent can be negative 15. The exponent can be positive 16. I know it's a little bit backwards from the other one, but that's okay. So what does that mean? What is the smallest number I can store? What's the smallest exponent? Would be negative 15. Right? Because what happens when I subtract 115 from that? I'm going to add 15 to that. That gives me my 0. And remember, what I'm storing is 0 up to some positive number. So negative 15 is the smallest thing because I'm adding 15 to that, and 0 is the smallest thing I can actually store as a characteristic. So that's negative 15. Can't go any smaller than that. The exponent, okay, let's say it's all zeros over here, the mantissa. And my exponent, let's not worry about sign. Sign doesn't really matter here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That looks like it might be 0, but truthfully, remember, we got to put the 1 back. So that's actually 1.0 times 2 to the negative 15. It's a small number, and that's the smallest number we can store, but it's not 0, is it? There's really no way to store a 0 here. So we have to have some special numbers, and 0 is one of those special numbers. And usually, those special numbers, all these special numbers actually, look at this field and this field. They look for special conditions there. So 0, if you look at these fields and you say, hey, that's all zeros, they go, oh, that might be a 0. And you look at this and it's all zeros, then the hardware or the software, the thing looking at it is supposed to treat this as a 0. That's our first special number. Now notice there is a positive and negative 0 because it doesn't look at the sign, it just looks at these things. So if this is all 0 and that's all 0, the number's 0. We're going to treat it like a 0, not like 2 to the negative 15, which means we can't use 2 to the negative 15. Right? We can't use that as one of our numbers either. So now our new smallest number is different. So I care that you know how 0 works. 0 is all zeros and all zeros. I don't care if you know the rest of these. Right? Special numbers use patterns of zeros on the mantistic. You cannot use all zeros in the characteristic. You cannot use all zeros in the mantissa. So that means we can't use this as an official number because it's officially one of those that it's looking for. So 0, there's something called denormalized. If you, and I don't really care about all these, to tell you the truth, so we're not going to go through them too much. The big thing about something like infinity, if you do like a division that's too big to fit, if you divide 240 billion by 1 or by a millionth, it's going to be too big to fit in the space, right? It's kind of like an overflow, but we don't want the hardware to error out on an overflow. We don't want it to break the computer if you try to divide something that's too big. So it has to have a way of telling you, hey, by the way, I didn't really store that number. This number isn't correct. The number was too big to fit. And the way it does that is it signifies infinity. So that's the point behind having an infinity in there. It's basically signaling, hey, an overflow occurred without actually erroring out any of the hardware or anything. And not a number is kind of the same thing. And that's the end of the slide. So we're done with all these.